There is a pinnacle of earthly engineering currently screaming through the absolute silence of the inner solar system. It is a delicate assembly of metal and silicon, forged by human hands, and it holds the record as the fastest object ever created by our species. Right now, it is tearing through the vacuum of space at a staggering velocity of over 400,000 miles per hour. To understand what that speed truly means, we must bring it down to a scale our minds can actually grasp. If you were traveling aboard this solar probe here on Earth, you could cross the entire width of a massive continent in mere seconds. You could watch the widest oceans vanish beneath you in the time it takes to draw a single breath. It is a velocity so extreme that it borders on the incomprehensible, stripping away our everyday intuition about distance and travel. A craft moving at this pace turns the enormous globe of our home planet into a fleeting blur. Yet, this blistering pace was not achieved simply by igniting a massive amount of chemical fuel and pointing a rocket at the dark. Instead, it is the result of decades of patient mathematics and careful orbital choreography. Engineers used the planets themselves as stepping stones, plotting a course that allowed the probe to steal momentum from neighboring worlds. Through precise gravitational maneuvers, the spacecraft approached massive planetary bodies, diving deep into their invisible gravitational wells. Like an acrobat catching a swinging trapeze, the probe swung around these worlds, using their immense orbital motion to catapult itself forward with ever-increasing speed. It is a masterpiece of celestial mechanics, a triumph of human ingenuity that pushes the absolute boundaries of what is physically possible with our current technology. And yet, when we turn our gaze away from our local neighborhood and look towards the wider galaxy, our greatest triumph suddenly feels agonizingly inadequate. Despite this incredible achievement, the cosmos remains overwhelmingly vast and entirely indifferent to our efforts. If we were to point this record-breaking machine away from the sun and aim it toward the very nearest star system, the journey would still require over 6,000 years. Pause for a moment and consider the crushing weight of that time span. 6 millennia ago, the first written languages were just beginning to emerge, and the pyramids were not even a dream in the minds of ancient architects. Entire empires have risen, conquered, crumbled to dust, and been entirely forgotten by history. In a fraction of the time it would take our fastest creation to cross the gap to our closest stellar neighbor. The sheer scale of the interstellar void transforms our greatest speed into a slow, frozen crawl. Imagine a solitary traveler departing on this journey, living their entire life moving faster than any human has ever moved. They would spend their youth, their adulthood, and their twilight years staring out into an unchanging pitch-black abyss. The stars would not streak past their window like rain. They would remain perfectly fixed, cold, and endlessly distant, mocking the traveler's relentless velocity. By the time that traveler breathed their last breath after a long, full human lifetime of 80 years, the ship would have covered barely 1% of the required distance. More than 99% of the dark ocean would still lie ahead, untouched, silent, and immensely cold. The void between the stars is not just an empty space. It is a formidable physical barrier, an impossibly wide moat of darkness that isolates every star system from the next. It forces us to confront a humbling reality about our place in the universe. Our ultimate speed, the absolute limit of our current mechanical might, is little more than a whisper against the roaring distances of the cosmos. We remain isolated on the shoreline of a dark cosmic ocean, realizing that the nearest island is further away than our minds can truly comprehend. Let us shift our gaze from the ultimate peak of our velocity to the absolute limit of our endurance. For nearly half a century, our most distant mechanical emissary has been plunging continuously outward into the endless night. Launched during the late 70s, it has never paused, never altered its fundamental purpose, and never looked back. While generations of humanity have lived, struggled, and passed away on our warm blue world, this solitary explorer has known nothing but the steady deepening of the dark. It has flown past the majestic gas giants, survived the bitter, freezing cold of the outer rim, and pressed onward into regions where the sun is merely the brightest star in an ocean of black. A few years ago, it crossed an invisible threshold that marks a profound milestone in the history of our species. It officially slipped beyond the protective magnetic bubble generated by our sun, leaving the familiar solar wind behind. For the very first time, a physical object forged by human hands tasted the undisturbed currents of true interstellar space. It is now sailing out through the ancient plasma that fills the voids between the constellations, completely exposed to the harsh, ancient cosmic weather of the wider Milky Way. Yet, this historic crossing carries a deeply sobering caveat regarding the true architecture of our celestial neighborhood. Escaping the magnetic breath of our star is not at all the same as escaping its immense gravitational grip. Despite its decades of relentless outward flight, the machine remains firmly tethered to our solar system by an invisible, unbreakable leash. Far beyond the orbit of the furthest known planets lies a vast, spherical shell of icy debris, left over from the violent dawn of creation. This distant, ghostly halo of comets represents the true gravitational boundary of our home, and the probe has barely even begun to scratch its inner edge. Current astronomical models suggest it will take approximately 3 centuries just to reach the thickest part of this icy shell. Furthermore, it will require perhaps 30,000 years to finally emerge from its outer boundary and truly leave the sun's domain. The scale of this reality is almost too vast for the human brain to comfortably process. Think about the immense span of time since the 1970s, the sheer volume of human history written during those decades of flight. Now consider the absolute fundamental speed limit of the universe. The total, astounding distance this remarkable machine has covered in nearly 50 years of continuous travel is a gap that a beam of light casually leaps across in less than one single earthly day. Imagine standing on the cold metallic hull of this distant wanderer. Right now, surrounded by an isolation so absolute, it would press against your chest. If you were to look back toward the center of the system, you would not see a warm, life-giving disk of fire. You would see only a piercing point of brilliance, entirely devoid of any noticeable heat, lost among a billion other points of light in the unending black. The radio signals sent back to Earth from this lonely vantage point whisper across the void, growing fainter and more fragile with every passing year. Soon, its decaying nuclear heart will lack the warmth required to power its delicate instruments, and its electronic voice will fall silent forever. It will no longer be an active explorer, but rather a drifting, frozen artifact of a curious species. This silent monument will continue to coast through the dark, preserved perfectly in the vacuum, carrying its golden records and greetings to an empty audience. It will wander blindly through the galactic wilderness for tens of thousands of years without ever brushing past another star. The machine stands as a breathtaking testament to our profound desire to reach out, while simultaneously highlighting the paralyzing enormity of the cosmic stage. Our longest, bravest journey is, in stellar terms, barely a single hesitant step away from our own front door. To understand why our deepest ventures into the dark remain so agonizingly slow, we must examine the very nature of how we throw mass into the void. For over a century, our fundamental method of leaving the ground has remained conceptually unchanged. Every traditional rocket ever built operates on a remarkably primitive, yet violently effective principle. It generates thrust by igniting highly volatile substances in a controlled explosion and throwing the resulting exhaust backward at the highest possible velocity. As the superheated gases roar out of the nozzle in one direction, the heavy vehicle is pushed violently in the opposite direction. This fiery process has carried us to the moon, built enormous orbital outposts, and flung our mechanical emissaries toward the outer planets. But when we turn our ambitions toward the terrifying gulfs between the stars, this fiery method crashes headlong into an insurmountable mathematical barrier. The core of this problem lies deeply embedded in the fundamental limits of chemical combustion itself. No matter how brilliantly we engineer the engines, or how exotic the volatile propellants we mix, a chemical reaction can only release a finite, stubbornly limited amount of energy. This hard physical limit dictates a maximum possible velocity for the exhaust escaping the rear of the rocket. Because the exhaust speed is fundamentally capped, the only way to make the vehicle go faster is to throw more mass out the back. To carry more mass to throw, you must build bigger tanks, which instantly makes the entire vehicle significantly heavier. Now, the engines must work harder just to push the unburned fuel itself, demanding even more propellant, in a vicious self-defeating spiral of diminishing returns. Imagine trying to cross a vast, deadly desert in a heavy vehicle, knowing that the only way to carry enough water for the journey is to tow massive trailers of water behind you. The sheer weight of the trailers causes the engine to burn more fuel, forcing you to tow even more trailers until the entire endeavor collapses under its own massive, absurd weight. This is precisely the tyranny of the rocket equation, and its mathematical reality is utterly brutal. Suppose we possess the sheer audacity to attempt accelerating a small, robotic probe to just 1% of the speed of light, using our very best chemical engines. Calculations based on standard physics show that the required mass of fuel does not just become impractically large, it becomes physically impossible. The numbers grow so exponentially huge that they cease to have any meaningful connection to human engineering or earthly resources. To achieve that modest fraction of light speed through chemical combustion alone, you would need more volatile propellant than the entire combined mass of the observable universe. Every star, every planet, every swirling nebula we can see with our most powerful telescopes, completely converted into rocket fuel, would still not be enough to reach that velocity. This astounding realization forces a profound shift in our understanding of deep space travel. Our failure to cross the interstellar voids is not a simple engineering problem waiting for a clever new design or a slightly better alloy. It is a fundamental, unbreakable constraint imposed by the strict laws of physics and the inherent weakness of chemical bonds. We are attempting to cross an ocean using nothing but the energy stored inside a matchbook. The violent pillars of smoke and fire that launch our modern miracles are simply the wrong tools for the vastness of the cosmic dark. If we are ever to break free from our localized neighborhood, we must abandon the explosive chemistry that brought us this far. The prison of chemical propulsion binds us tightly to the inner system, and the keys to escaping it must be forged from entirely different principles of physics. If the violent infernos of chemical rockets are fundamentally insufficient, we must turn our hopes toward more exotic methods of generating forward momentum. Engineers and physicists have spent decades dreaming up alternative engines, searching for clever ways to bypass the brutal tyranny of conventional fuel. One of the most successfully realized concepts is the ion drive, a technology that feels as though it was pulled directly from the pages of science fiction. Instead of burning volatile chemicals in a chaotic explosion, an ion drive uses powerful electric fields to strip electrons from an inert gas. These newly charged particles are then accelerated through a magnetic grid and fired out the back at astonishingly high velocities. Because the exhaust speed of these invisible particles is vastly higher than chemical flames, the engine uses its propellant with incredible, elegant efficiency. However, this remarkable efficiency comes with a deeply frustrating trade-off. While the stream of particles is incredibly fast, it is also incredibly sparse, resulting in a physical push that is astonishingly weak. If you were to hold a firing ion engine in your hands here on Earth, the total thrust it generates would feel roughly equivalent to the gentle weight of a single piece of paper resting on your palm. In the friction-free vacuum of deep space, this delicate push can indeed build up enormous speed, but it requires months, years, or even decades of continuous operation to achieve it. Their gentle, whispering thrust is brilliant for slowly maneuvering satellites or nudging probes towards the asteroid belt, but it absolutely cannot solve the brutal mathematics of interstellar distance. Realizing that we need both high efficiency and massive thrust, designers have looked toward the tremendous power locked inside the atom itself. Nuclear thermal rockets represent a significant conceptual leap forward in spacecraft propulsion. Instead of relying on chemical combustion, these massive engines use a highly controlled nuclear fission reactor to generate intense blistering heat. Liquid hydrogen is pumped directly through the glowing reactor core, instantly flashing into a superheated gas and exploding out of the nozzle. This raw atomic heat effectively doubles the exhaust velocity achieved by the very best chemical engines ever built. During the height of the Cold War, prototypes of these engines were actually constructed and tested, shaking the ground with their immense radioactive roar. They represent perhaps the most powerful propulsion technology we could realistically build with current industrial capabilities. Yet, when we plot a course to the stars using the theoretical maximum performance of a nuclear thermal rocket, the vastness of the cosmos mocks us once again. Even with this massive leap in capability, and even utilizing the most optimistic mission profiles imaginable, the transit times remain paralyzing. A journey to the nearest neighboring stellar systems would still require tens of thousands of years of drifting through the dark. Generations would be born, live entirely within the metallic confines of the vessel, and die without ever seeing a planet larger than a pinpoint of light. The engines would fall silent centuries before the destination was reached, leaving the ship coasting silently through the empty void. Despite harnessing the very fires that power the suns, we find ourselves unable to cross the gaps between them in any meaningful time frame. The stark reality of these alternative engines reveals the true depth of our isolation. Humanity remains seemingly trapped within a tiny, fragile bubble, restricted to wandering within just a few light hours of our isolated home world. The stars above continue to shine their cold, indifferent light down upon us, seemingly forever beyond the reach of our cleverest machines. When every internal source of power falls drastically short, the only remaining option is to leave the heavy engines and massive fuel tanks behind entirely. This radical shift in thinking has led scientists to seriously consider a concept that sounds almost mythical, riding on pure beams of light. The core idea centers around deploying large, incredibly thin, reflective sails in the vacuum of space. While light possesses no resting mass whatsoever, the fundamental laws of physics dictate that it does carry momentum. When a photon strikes a highly reflective surface and bounces off, it transfers a tiny, almost imperceptible physical push to the material. If you construct a sail large enough and make it incredibly lightweight, this microscopic pressure can theoretically harness the momentum of billions of photons to accelerate a spacecraft. Because the vessel carries absolutely no fuel of its own, it escapes the crushing mathematical tyranny that doomed traditional rockets. However, the faint light from our distant sun is far too weak to push a sail to interstellar velocities. To achieve meaningful speed, we would need to construct massive, highly synchronized ground arrays consisting of thousands of powerful lasers here on Earth. These sprawling installations would draw gigawatts of electrical power, focusing an intense, blinding beam of coherent energy directly onto the distant sail. By concentrating this continuous barrage of photons against a tiny gossamer probe, weighing only a few grams, the acceleration achieved would be violent and extraordinary. Theoretical models suggest that this focused energy could push these tiny mechanical explorers to an astounding 20% of the speed of light within minutes. At that blistering pace, the previously insurmountable gulf between the stars suddenly begins to look manageable. These fragile, speeding probes could cross the vast dark and reach neighboring stellar systems within a mere couple of decades. For the first time in human history, we could receive close-up images from another solar system within a single human lifespan. It is a breathtaking vision of exploration, but this brilliant concept conceals a deeply fatal flaw. The very mechanism that allows the probe to reach such incredible speeds guarantees that it can never stop. Because the craft left all its heavy propulsion systems and fuel behind, it possesses an absolute inability to slow down upon arrival. There is no laser array waiting in the destination system to fire a decelerating beam against the front of the sail. After spending 20 years rushing silently through the empty void, the dramatic encounter would be over almost before it began. The travelers, whether they were tiny cameras or microscopic sensors, would flash violently through the target system in a matter of minutes. They would capture whatever frantic glimpses they could, as alien planets blurred past their lenses at a fifth of light speed. And then, just as suddenly as they arrived, they would shoot past the outer planets and disappear back into the unending void forever. They would become eternal ghosts, destined to drift endlessly outward, unable to ever alter their course or report back again. While light sails offer our most realistic chance of touching another star, they restrict us to the role of fleeting, hyperfast spectators, rather than true explorers. The dream of arriving, entering orbit, and quietly studying an alien world remains fundamentally incompatible with riding on beams of light. If we insist on building a heavy vessel capable of slowing down and stopping at its destination, we must find the absolute most concentrated source of energy the universe allows. We must abandon the weak bonds of chemistry and the heavy infrastructure of nuclear reactors, and look toward the theoretical perfection of antimatter. To understand antimatter, one must realize that for every fundamental particle that builds our everyday world, the universe allows an exact opposite mirror image to exist. An antiproton looks and behaves precisely like a normal proton, but it carries a negative electrical charge instead of a positive one. When a particle of normal matter comes into physical contact with its opposite counterpart, something violently absolute occurs. They do not simply burn or break apart, they annihilate each other completely, erasing their physical existence from reality. In that dramatic instant of mutual destruction, they convert their entire combined mass directly into pure, unadulterated energy. There is no ash left behind, no wasted byproducts, and no unburned remnants to carry along as dead weight. This spectacular reaction is hundreds of times more powerful than the chaotic fusion raging inside the core of our sun, and vastly superior to our best nuclear fission. It is the ultimate limit of energy density allowed by the rigid laws of physics, a perfect conversion of matter into moving force. If engineers could somehow harness this explosive annihilation and direct the resulting gamma rays out the back of a nozzle, the thrust generated would be staggering. Such extreme, flawless efficiency could theoretically accelerate a massive, heavy spacecraft to a highly significant fraction of light speed. It would finally allow a crewed vessel to cross the dark ocean, carry the necessary shielding, and still possess the immense power needed to safely decelerate upon arrival. It sounds like the perfect, ultimate solution to the interstellar problem, an elegant key to unlocking the wider galaxy. However, this beautiful theory shatters violently when we confront the grim realities of manufacturing and containment. Antimatter does not simply exist in natural, easily accessible pools waiting to be mined or pumped into a tank. Because it instantly destroys itself upon touching anything in our normal universe, it must be created artificially, one painstaking particle at a time. The insurmountable obstacle lies in manufacturing this incredibly exotic fuel through massively expensive, highly energetic particle collisions. Currently, we create tiny fractions of antimatter by smashing protons together at near light speed, inside massive, multi-billion-dollar underground rings. The electrical energy required to run these gigantic machines is staggering, yet the resulting harvest is almost laughably small. If we were to gather every single antiproton humanity has ever managed to create since the dawn of particle physics, it would not even be enough to boil a single cup of water. The brutal economics of this process dictate that antimatter is, by an enormous margin, the most expensive substance that has ever existed. Producing enough fuel for just one single crewed mission to a neighboring star system would require humanity to completely drain its resources. We would need to dedicate the entire global energy grid, saving our current electrical output continuously for billions of years. Even if we somehow solved the manufacturing nightmare, we would face the terrifying challenge of safely storing tons of a substance that detonates upon touching the walls of its own tank. The theoretical perfection of antimatter remains exactly that, a flawless mathematical dream safely locked away behind an impossibly steep wall of energy economics. It taunts us with the ultimate answer, while ensuring we can never afford the price of admission. Faced with the seemingly impossible mathematics of mass, fuel, and immense distances, it is easy to succumb to a deep, permanent pessimism regarding deep space travel. For a long time, early scientists believed the vast, empty distances between stars acted as a permanent, unbreakable cosmic quarantine. They assumed that the universe was a static stage, a rigid box where a mile was always exactly a mile, and a ticking second was always exactly a second. Under those rigid rules, human lifetimes are simply too incredibly short, and the gulfs of space are entirely too vast for any biological creature to cross them. But exactly this rigid classical assumption was brilliantly shattered at the dawn of the 20th century. A young patent clerk named Albert Einstein looked at the fundamental nature of light and realized that the old masters of physics had misunderstood the stage entirely. He shattered the long-held assumption of absolute space and time by revealing that distance and time are actually completely flexible. His revolutionary insight began with one strange, unyielding rule. The speed of light in a vacuum must always remain perfectly constant, regardless of who is measuring it or how fast they are moving. If you chase a beam of light at half its speed, you might logically expect the light to appear to be moving away from you slower than usual. But Einstein realized this is not what happens. The beam still pulls away from you at exactly the speed of light, as if you were standing perfectly still. For this bizarre mathematical reality to hold true, something else in the equation must bend and stretch to compensate. Because the speed of light refuses to change, time itself must slow down for a moving observer. This is not merely a psychological trick of perception or a mechanical flaw in the measuring devices. This mathematical reality means that clocks aboard a speeding vessel literally tick significantly slower than those left sitting quietly at home. The faster the ship moves, accelerating closer and closer toward the absolute cosmic speed limit, the more dramatically the flow of time stretches out. Furthermore, as time slows down, the physical distance the traveler needs to cross actually compresses, shrinking along the direction of travel. To the people watching from Earth, the ship might take 10 years to cross a certain distance, moving just under the speed of light. But to the astronauts aboard that speeding vessel, their clocks, their beating hearts, and the aging of their very cells experience a completely different reality. They might measure the exact same journey as taking only a few short months, arriving perfectly healthy while a decade has passed back home. This stunning phenomenon transforms the ultimate limits of human exploration from a biological impossibility into something entirely achievable. The universe is not a rigid box built to keep us quarantined forever. It possesses a strange built-in mechanism that allows the short-lived to travel incredibly far. By exploiting this bizarre loophole in the very fabric of reality, we might one day outrun our own mortality. The key to reaching the deepest stars is not simply building a faster engine, but learning how to manipulate the flowing river of time itself. To fully appreciate the strange power of this temporal loophole, we must run the numbers and see precisely what happens as a ship approaches the absolute limit. The effects of this phenomenon are not linear. They do not increase steadily, but rather curve upward dramatically as you push closer to the edge. At roughly 90% of the speed of light, the mathematics of the universe dictate that time passes more than twice as slowly for the traveler. For every 2 years that slowly tick by on the calendars back on Earth, the speeding astronaut experiences only one single year of actual life. This alone is a profound advantage, effectively doubling the physical reach of a standard human lifespan without altering the biology of the crew. But the true, almost magical power of relativity reveals itself only when we push the engines to their absolute extreme limits. If a vessel could somehow accelerate to 99.9% of light speed, the compression of reality becomes incredibly drastic. At this blistering pace, the flow of time for the traveler slows to a mere crawl compared to the universe rushing past outside their reinforced windows. Pushing closer to this absolute limit compresses decades of earthly time into mere months of subjective experience for those aboard the ship. A journey to a star system 50 light years away would normally take 50 years of continuous travel from the perspective of the people who launched the mission. But the astronauts aboard would feel only a little over 2 years pass, watching their hair grow only slightly while an entire generation ages back home. This stretching of time means that even the most terrifying galactic distances suddenly fall within the realm of biological possibility. If a ship could maintain a constant acceleration of one earthly gravity, pressing the crew comfortably into their seats, the results become staggering. A journey to the very center of our galaxy, a swirling, chaotic region tens of thousands of light years away, could actually be completed within a single human lifespan. The astronaut would age perhaps 20 years, while on Earth, entire civilizations would rise, fall, and be swallowed by dust over tens of millennia. If we push the mathematics even further, the numbers become truly dizzying and hard to anchor to everyday reality. A traveler could theoretically cross the dark, empty void to our neighboring Andromeda galaxy, while aging only a few short years in their acceleration couches. They would arrive perfectly healthy and ready to explore, while more than 2 million years of brutal, unforgiving history played out back on their home world. The universe, in its strange and deeply non-intuitive construction, provides a natural mechanism that allows human consciousness to span millions of light years. We are not inherently locked out of the deepest cosmos by our short, fragile biological lifespans. The fabric of reality itself bends to accommodate velocity, offering a path that allows us to step across the stars, provided we are willing to pay the ultimate price. The ability to stretch time and compress distance feels like a miraculous cheat code woven directly into the fabric of reality, a gift allowing us to conquer the stars. But the universe rarely offers such profound advantages without demanding an equally profound and often devastating payment in return. The very same equation that allows time to slow down also enforces a brutal, unforgiving penalty regarding the physical mass of the moving object. Einstein's realization of the strict equivalence of mass and energy creates a massive physical barrier for anyone attempting to move at high velocities. As an object accelerates and pushes closer toward the absolute cosmic speed limit, it behaves mathematically as though it becomes exponentially heavier. It does not literally gain more atoms, but its resistance to further acceleration increases so dramatically that it requires vastly more force to push it just a tiny bit faster. At low speeds, adding a bit more energy gives you a predictable increase in velocity, a simple, intuitive exchange that governs our everyday lives. But as the ship approaches 90% of light speed, this simple exchange completely breaks down. Every additional small increment of speed now requires vastly more energy than the one that came before it, following a punishing, upward curving mathematical wall. To push a massive ship from 99% to 99.9% of light speed demands an absolutely staggering, almost incomprehensible amount of power. Calculations show that accelerating even a relatively small, modestly equipped crewed vessel to these time-dilating speeds requires numbers that dwarf human comprehension. You would need roughly the total energy output generated by our sun shining brightly for several months, focused entirely into the engines of a single ship. And this terrifying requirement only covers the energy needed to actually leave our solar system and reach the necessary cruising speed. The true horror of this energetic debt reveals itself when the travelers finally approach their distant destination. To avoid flashing violently past the target star and disappearing into the void forever, the ship must turn its massive engines forward. Decelerating the incredibly heavy, fast-moving vessel at the destination requires exactly the same staggering amount of energy all over again. The temporal loophole is very real, and the mathematics governing it are perfectly sound and proven. However, accessing that loophole requires a civilization capable of casually wielding the raw, unchecked power of entire stars. The universe allows us to cheat our biological clocks, but it strictly demands that we pay for that privilege with an astronomical amount of energy. Until we master the ability to harness and focus the fires of the cosmos itself, the relativistic dream remains locked firmly behind a wall of sheer, brutal physics. Even if a highly advanced future civilization managed to harness the staggering energy required to push a heavy vessel to the brink of light speed, the challenges of the journey are far from over. The act of moving so incredibly fast through the cosmos fundamentally alters the traveler's relationship with the environment outside their fragile hull. The asymmetrical experience of acceleration means the traveler ages significantly less than the people left behind, a fact that forces a profound psychological burden upon the crew. They must accept that every single second they spend rushing through the dark severs them further from the world they knew and the people they loved. This temporal disparity is not merely a theoretical curiosity debated by mathematicians on blackboards. It has been physically proven using precise atomic clocks, flown on commercial jets around our planet, which recorded tiny but measurable differences compared to clocks resting quietly on the ground. While the psychological weight of this temporal separation is immense, the physical dangers waiting in the void are immediate and potentially lethal. Space is commonly described as a perfect empty vacuum, but this is an absolute misconception. The interstellar medium is littered with stray hydrogen atoms, microscopic grains of ancient dust, and the occasional larger fragment of rocky debris. When you are drifting slowly through the system, these tiny particles gently bounce off the hull, causing absolutely no measurable damage. But at extreme relativistic velocities, the almost empty space between stars violently transforms into a deadly, highly energetic radiation environment. As the ship tears forward at near light speed, it slams into these stationary particles with terrifying, devastating kinetic energy. A microscopic grain of dust hitting the ship at 99% of light speed carries the explosive equivalent of several tons of conventional explosives. The forward-facing sections of the vessel would be subjected to a continuous, blistering bombardment that would quickly vaporize conventional metal alloys. Surviving this relentless, invisible storm requires massive physical shielding, perhaps a thick block of ice or dense rock pushed ahead of the living quarters. Alternatively, it demands the deployment of highly advanced magnetic deflection systems, creating an invisible wedge to sweep the deadly particles aside before they can strike the hull. If the shielding fails for even a fraction of a second, the resulting catastrophic impact would instantly obliterate the delicate human cargo within. The universe strictly punishes those who attempt to cross its vast oceans too quickly, turning the very emptiness of space into a lethal glowing hazard. A relativistic journey is not a peaceful, quiet glide through the dark, but a violent, extremely noisy battle against the scattered remnants of creation. The faster we try to run, the harder the universe pushes back, demanding perfection from our engineering and immense courage from those who dare to make the crossing. While we struggle with the immense engineering challenges of reaching nearby stars, a much larger, darker reality is quietly unfolding on the grandest cosmic scales. When we look out into the deep void, it is tempting to view the universe as a vast, unchanging landscape waiting patiently for us to eventually build the right ships. But the universe is not a static canvas. It is a highly dynamic, actively evolving entity that is constantly stretching itself outward. The very fabric of space is expanding, and this expansion carries distant galaxies away from us at terrifying, ever-increasing speeds. This mysterious accelerating expansion creates absolute fundamental horizons that no amount of advanced technology or infinite energy can ever overcome. To understand this chilling reality, you must imagine drawing dots on a deflated balloon and then slowly blowing air into it. The dots do not move across the rubber, but as the rubber itself stretches, every dot moves further away from every other dot. In our universe, the space between the galaxy clusters is stretching precisely like that rubber, and the further away a galaxy is, the more stretching space exists between us and them. Beyond a certain staggering distance, there is so much expanding space between us that the total stretching effect happens faster than the absolute cosmic speed limit. This means that the light from those incredibly distant galaxies, desperately trying to cross the expanding gap, is moving toward us like a runner on a treadmill that is spinning too fast. The light will simply never reach us, and consequently, we can never ever reach them, even if we possessed a magical ship capable of moving at exactly the speed of light. This creates an invisible spherical boundary around our local cosmic neighborhood, a strict physical limit to what we can eventually interact with. Right now, as you listen to this, galaxies are quietly slipping over that edge, crossing the horizon and fading away from our view forever. Regions of the cosmos that are visible to our best telescopes today will eventually become permanently inaccessible to any future traveler, regardless of how advanced their propulsion systems become. Every single second that ticks by, more of the distant universe becomes forever unreachable, locked away by the relentless expansion of space itself. The window of opportunity for exploring the wider cosmos is slowly, silently, but continuously closing forever. Trillions of years in the far future, the night sky will be entirely empty, save for the few stars that are gravitationally bound to our local cluster. Future astronomers, looking out from their isolated worlds, will see nothing but an endless, impenetrable black void in every direction. They will never know that a wider universe full of billions of galaxies ever existed, because the evidence will have been stretched away beyond the absolute horizon. We happen to live in a privileged temporary era where the grand architecture of the cosmos is still brightly visible and theoretically reachable. But that era is firmly scheduled to end, and the universe is slowly pulling the curtains closed on the greatest stage we have ever known. When we step back and look at the terrifying energy requirements, the brutal physical hazards, and the unforgiving mathematics of time dilation, a profound realization emerges. Relativistic voyages differ fundamentally from any era of earthly exploration because they completely sever all meaningful connections to the traveler's original time. Deep space travel shatters this continuity completely, turning every departure into an irreversible jump into an unknown future. Returning from a relativistic deep space journey to a distant star does not mean coming home to a slightly older family. It means arriving hundreds, or perhaps thousands of years in the distant future of your home planet. There is even the terrifying possibility that the launching civilization might have completely vanished, leaving the returning astronauts as the last, lonely remnants of a dead era. Every relativistic departure, no matter how scientifically vital or heroically executed, acts as a permanent, one-way exile into a deeply unfamiliar temporal reality. The astronauts who agreed to crew these hypothetical vessels must be willing to attend the funeral of their entire world the moment the engines ignite. They are not simply explorers pushing the boundaries of the map. They are temporal ghosts, deliberately cutting themselves out of the flowing timeline of their species. This ultimate cost forces us to confront a deeply philosophical question about what it actually means to explore. Is the gathering of distant data and the planting of flags on alien soil worth the absolute sacrifice of human connection? If we build the perfect engine, harness the power of stars, and conquer the brutal distances of the dark, we will gain the universe, but lose our home. We must ultimately choose between the boundless, glorious range of physical exploration and the deep, anchoring human need for continuity and connection. The stars offer us an infinite canvas of wonders, but they demand that we leave everything we know behind, forever, to see them. Perhaps the ultimate barrier to deep space travel is not the rocket equation, nor the energy requirements, nor the lethal dust waiting in the void. Perhaps the true barrier is simply the weight of the human heart, unwilling to trade the warmth of its own era for the cold, timeless glory of the distant dark.